Hello everyone, welcome to the worksheet walkthrough for week 3. The first question has us prove a lot of facts about planar graphs, and the first one we'll prove is Euler's formula, or v plus f is equal to e plus 2. So the proposition that we want to prove is that for all graphs, v plus f is equal to e plus 2 holds. If we want to prove something is true for all types of something, that's a hint to use induction. And generally with graphs, there are two different types of induction you can do. You can do inductions on vertices, or more commonly, we do induction on edges. And we usually induct on edges because there are far fewer edge cases to worry about compared to vertices. So indeed, we're going to proceed by induction on e. And our base case is the first natural number, or e is equal to 0. So we want to show that v plus f is equal to e plus 2 holds for all graphs with 0 edges. So the only graph that has 0 edges, that is still a graph, is the graph with one vertex. And so we can plug in the numbers v is equal to 1, f is equal to 1, and e is equal to 0. And indeed, we can show that that equality does hold. So that's our base case. For our inductive hypothesis, we're going to suppose that for some larger k is greater than or equal to 0, any graph with k edges satisfies v plus f is equal to e plus 2. And this is important because we're going to use this information in the inductive step later. For the inductive step, we're going to consider any graph with k plus 1 edges, and then we're going to remove an edge to perhaps use the inductive hypothesis, and then we're going to add it back, and we're going to still show that that equation holds. And it turns out there are kind of two cases for every type of graph with k plus 1 edges. Either the graph is a tree or it's not a tree, and there's no in between. A graph is either a tree or not a tree. So for case 1, let's suppose G is a tree with k plus 1 edges. And so we can say that the number of vertices is still v. Trees only have one face, and the number of edges, in this case, it's actually k plus 1. And because trees have a special relationship between vertices and edges, we actually know that the number of vertices, we can be more specific, it's k plus 2. And so let's just plug it in and see if this holds. So this is the statement that we want to show. We want to show that if we substitute e for k plus 1, that equality still holds. So we're going to substitute v for k plus 2 and then k plus 1 for e. And indeed, we do get k plus 3 is equal to k plus 3. So that equality holds. And notice that in this case, we actually did not use the inductive hypothesis. It's in case 2 that we need to use the inductive hypothesis. So in case 2, the graph with k plus 1 edges is not a tree. So if it's not a tree, then the graph is guaranteed to have a cycle. And it turns out we're going to remove an edge that was creating that cycle. And if we do that, we don't get any disconnected vertices. And again, the proposition that we want to show in the inductive step is v plus f, whether it's equal to k plus 1 plus 2 or not. So indeed, every graph that's not a tree has a cycle, so we can always remove an edge of the cycle. For example, for this graph, we can perhaps remove this edge right here. And if we remove it, notice that we reduce the number of faces by 1, and also the number of edges by 1. So this new graph G prime has f minus 1 faces, and instead of k plus 1 edges, we now only have k edges. And moreover, by the inductive hypothesis, we know that all graphs with k edges satisfy Euler's formula. So we can substitute the values we have for the G prime graph, and we know that this equality is true. Now we're going to add the edge back. So now we're going to get any possible graph with k plus 1 edges. And now the thing we wanted to show, v plus f is equal to k plus 1 plus 2, that equality holds for all graphs because we can just add 1 to both sides of our equation that we got from the inductive hypothesis. So there we go. The claim is proven. Hello everyone. Let's do number 2 and number 3 now, which prove various inequalities about planar graphs. So the first result that we'll prove is if a graph is planar, then it implies the number of edges is less than or equal to the 3 times number of vertices minus 6. So the intuition behind providing the inequality like this is, let's suppose that we have some planar graph. For example, this planar graph right here. If this planar graph has too many edges, then there's for sure going to be an overlap somewhere. And then that would mean that the graph is not planar anymore. So because this is the case, we want to bound the number of edges in relation to the number of vertices. And then we'll know that this inequality holds for any type of planar graph. And if we manage to prove this, we can also state the contrapositive, which is if E is greater than 3V minus 6, that means the graph is not planar. So those are equivalent statements that we will prove. The first little bit of background information to prove this is the handshaking lemma for sides, which states that if we sum over all of the faces and the number of sides in those faces, the total number of sides in that graph is going to equal to 2 times E. So as an example, on the left-hand side, this graph has 4 sides. So it has 4 faces, So it has face number 1, face 2, face 3, and the outermost infinite face 4. And we know this, each one of these faces has a number of sides corresponding to it. So face 1 has 5 sides, for example. Face 2 has 3 sides. Face 3 similarly has 3 sides. And we know that this equality is going to hold because we have the number of edges in this graph is 10. You can check that by yourself. And then the number of total edges is 2 times 10. And this makes sense because whenever we have an edge, that edge contributes 2 sides to it. It contributes, for example, this edge contributes one of the sides on the outermost face and one of the sides on face 1. So now we've established the handshaking lemma for sides. And this is useful because we want to somehow relate the number of edges and we want to do some substitution. So now we're going to go on with the proof. We're going to suppose that G is a planar graph. And we also know that for every face in a planar graph has at least 3 sides. So S sub I is greater than or equal to 3 for all I. And to justify this, we can make the observation on any type of planar graph that every possible face has at least 4 sides. Otherwise, it's not a valid planar graph. Now, the only exception to this is the graph with only 2 vertices or the graph with 1 vertex. And so I should be more precise. I should say that every face in a planar graph with greater than 2 vertices has at least 3 sides. So yeah, so S sub I is greater than or equal to 3 for all I. So we can substitute. So we can bring this and we can substitute 3 as the lower bound. So we know that this is going to be upper bounded by 2 times E. And then we can do the algebraic manipulation to end up getting f is less than or equal to 2/3 e. And now, the formula that we have that relates the number of vertices and edges and faces is Euler's formula, which is v plus f is equal to e plus 2. So now we can substitute the f that we got from the previous results. And if we substitute, we're going to get v plus 2/3 e. We know this quantity is greater than the actual f, so this quantity is greater than e plus 2. And indeed, we do the substitution, we do the simplification, we do end up getting e is less than or equal to 3v minus 6. Now let's talk about the third result, which states that if a graph is planar and bipartite, so this is a stronger condition, we need the graph to also be bipartite. That implies a tighter bound. It implies e is less than or equal to 2v minus 4. So the derivation is pretty much the same as the left-hand side. It's just now we have the fact that each face has at least 4 sides now instead of 3. And that's because there are no faces with only 3 sides. A bipartite graph never has a face with only 3 sides because this face itself violates the bipartite property. For example, we have a white vertex connecting a white vertex. So any valid face in a bipartite graph must have at least 4 sides. And the rest of the proof follows the same as the proof for e is less than or equal to 3v minus 6. And we do end up getting e is less than or equal to 2v minus 4. All right, now we're going to do part 2, which is an application of Kuratowski's theorem. So Kuratowski's theorem states that a graph is not planar if and only if it contains K5 or K33. And K5 is the complete graph on 5 vertices, and K33 is a complete bipartite graph on 3 and 3 vertices. So just an illustration of K33. So we have 2 groups of vertices, and there is every possible edge in between these 2 groups. And the fact that no edges go between the same group makes this a bipartite graph. Okay, so that's just an example of a bipartite complete graph. And it turns out that because this is a strong if and only if statement, these 4 statements also hold. So you can notice that I took the converse, I took the contrapositive, and then I took the contrapositive of the converse. All right, let's get to actually modeling this problem. So we have a group of 6 friends. I'm just going to label them as vertices. And any one person is friends with the 2 individuals next to them, and also the person sitting directly across from them. So for example, person 1 is friends with person 6 and person 2, and also person 4 who is across from him. So I'm just going to do this for every single person until I run out of edges like that. And immediately we notice that we can actually partition this graph into 2 groups. So group 1 is going to be the green vertices, and group 2 is going to be the orange vertices. We notice that there are no edges between orange vertices, and also there are no edges between green vertices. So this is a bipartite graph. Also, each vertex has 3 edges, so the maximal number of edges is is hit in a bipartite graph. And this means that this is actually a complete bipartite graph with 3 edges in one group and 3 edges in the second group. So because the graph contains K33, that means that it is not planar. So that's the solution to this problem.